Go ahead and record. All right, so we're on to lecture 6, I believe, and we're continuing the review material. And this week will be the last week of the so-called review material. And today, I looked at the homework, what I posted for you guys for homework 3, and I felt like the estimability, it sounded like you guys didn't, either you didn't talk about it at all, or maybe very quickly in 6612. I didn't get a feeling like you had really talked about that very much. So estimability, it seems kind of weird in a way. It's like, what is this stuff? Why do we need to worry about it? Well, I think often what's done in 6612 is you're told, okay, there's linear dependencies. If you have a class variable in the model, you have an X matrix and you have linear dependencies, and there's obvious issues with that because that leads to a not full rank X matrix. And so you can't use the regular inverse when you're calculating beta hat. Now, you don't use X inverse directly, it's X transpose X inverse, but if X doesn't have full rank, then X transpose X doesn't have full rank. And X transpose X then doesn't have a regular inverse. So, these are technical issues, but we have to deal with the fact that the class variable that we enter, or multiple class variables, if you put in a column for every single level, then you don't have a full rank X matrix. That's the bottom line. And if you run proc GLM, you guys probably are familiar with that statement that you get, that you have a letter B besides a bunch of the rows, and it says, be careful, the X inverse cannot be solved. I forget exactly what it is, but you get a warning that that the X matrix doesn't have full rank, essentially. And so you have to consider that issue. And we talked about last time how, well, there's a few ways to deal with it. And the way that you guys probably are familiar with is you write a full rank matrix directly. So you figure out, I'm going to use an indicator for the levels except for one. One will be the reference level. And that's how you're taught. You just do it that way. But the way that the software actually works is that it puts in a level for, it puts in a column for every level of that class variable, and it uses a G inverse to a generalized inverse, which you can do even if X does not have full rank, and resulting in X transpose X that does not have full rank. And so you can use a G inverse of that. And in some cases, it ends up looking the same as if you would have set one of the levels to 0. But the thing is, there's multiple types of G inverses that you can use. And so this we talked about last time. That's kind of a review. So I'm doing a review of a review. And what I want to do today is just go through, before I go into the slides that we have planned, I want to talk about a couple things. The first is the estimability. And so let me share my screen here. Okay, so I wrote this up on Friday, and so this is, again, just to kind of get you up to speed. And in particular, because you had that homework question that that asked about estimability, so I wanted to get you up to speed on that. So so we'll consider, for simplicity, we'll just consider the general linear model. So when X does not have full rank, then beta hat is not unique. So for less than full rank models, we want to know what the linear combination of beta are estimable. You know, what things can we estimate in our model is essentially what that's asking. So when you say what combination of beta, okay, so we're talking about L beta. Okay, so there's some combination of the beta that we're looking at, and L is a vector. So we're talking about things that look like that, L beta, and we're interested in what form does what does L have to be? What linear combination of beta are estimable, which essentially means that they have this has a unique unbiased estimator. So when that L has a form A transpose X, in other words, when it's a linear combination of the rows of X, then L beta hat, we're going to talk about the distribution of this thing. Last time we talked about the distribution of just beta hat. It's going to do this to me again, apparently. So I'm going to fight it. So we're interested in the distribution of L beta hat. And like last time, for beta hat, we showed that we can use that linear form result to figure out the distribution. And so when L equals A transpose X, so there's some A. So it's basically saying that there's some linear combination of the rows of X and then beta hat, I think just for simplicity here, I'm just going to talk about the GLM case. Okay, it's going to be a similar issue for the linear mixed model, but for the GLM case, then we just have X transpose X inverse X transpose Y. Okay, and I think you guys probably talked about this. This thing right here, you may have heard it called the hat matrix. What I like to call it is a projection matrix, P of X. Okay, so either the hat matrix or the projection matrix. This thing is, regardless of the G inverse may not be unique, but regardless of that, this thing is unique for any G inverse. Okay, so there's certain properties that the projection matrix has. It's symmetric, it's idempotent, which means that if you multiply P of X times P of X, you get P of X. It's unique for any G inverse. And a lot of these properties I have, I lay out in the course notes. So you may have heard it called the hat matrix. I like the reason why I like to call it the projection matrix is because what you do is you're projecting usually Y. You're projecting it onto the column space of X, which is all linear combinations of the columns of the X matrix. And so intuitively, I think it kind of makes sense. So this thing, if we use that linear form result, we can show that actually, this thing is has a normal distribution, and its mean is L beta. Let's get rid of that. So the mean is L beta, and the variance is L x transpose x inverse L transpose sigma. That's for GLM. Okay, so you can show this using the linear form result that we talked about last time. Okay, so this is unique. So that's unique regardless of the G inverse. Now in the variance, you have the same issue. You have a G inverse here. So the question is, how do you know this thing is unique, this variance? What you can show pretty easily that if you plug in what L is, if it has that form A transpose X, then you can have a piece there that can be expressed as a projection matrix as well. So if you have so for the variance, you have L x transpose X inverse L transpose sigma squared. Well, that's just A transpose X, and then you have your X transpose X inverse. And then if you transpose A transpose X, you get X transpose A. So you can see that you end up with P of X again there. So that's, again, that's unique. So the whole point is that if you take a linear combination and L has this form A transpose X, then regardless of, even if the original vector beta is not unique, L beta is unique, okay? And the other thing is, this is important too. In this case, if L is equal to LH, that also will show you that the L beta that you're interested in is unique. So let's show this real quick. I know this stuff is kind of more technical, more, this is kind of, we're getting, this class is really a mixture of theoretical and applied, and now we're kind of in the theoretical stuff. But this gives us the tools that we need to analyze our data. So what H is that's just a for the GLM, that's this quantity. That's just an easy way to express that, okay? So we want to show that in this case, when L has this form, when it's a linear combination of the rows of X, then this is true. L is equal to LH. Okay, so let's start with LH. So if we have LH, then this is equal to A transpose X. And then H is, we're plugging in X transpose X inverse times X transpose X. Okay, so in that quantity, what do we recognize first? See if you guys are with me in this technical stuff. Yeah, go ahead, Jonathan.
The HAP matrix?
Yes. HAP matrix or projection matrix. So that's this interior quantity here. So we have A transpose and then that hat matrix or projection matrix times X, right? Now this is why I like the name projection matrix, because you think about projecting something into the column space of X, right? So it's applying, if you apply that projection matrix to X, what do you get? If you have, so think of a plane and think of a vector coming off of that plane and projecting a light. So you're casting a shadow onto that plane. That will, if the vector is not in the column space, it's going to change it. It's going to project it onto that column space. But what do you know about X?
Is it orthogonal?
Not orthogonal. You know, to be orthogonal, it has to be, it's not in there, right? It's not in that column space, right?
Mm-hmm.
So the column space of X is all the possible linear combinations of the columns of X, right? So what do you know about X as it relates to the column space of X?
Isn't it all on the same plane?
Yes, that's the correct answer. So X is in the column space of X, right? So if you're projecting something that's already in there, is it going to change it at all? No, it's not. So this is equal to A transpose X, because X is already in column space. You can't project, you're not going to change it. So Matt was right on that one. So it's A transpose X, that's equal to L. So we've shown that when L has a form A transpose X, then LH is equal to L. Why do we care about that? Well, this gives us a way to decide whether a linear combination of our parameters is estimable. That's it in a nutshell. So I'm gonna show you an example. The example here is we have a study where subjects in 3 groups are observed over 2 times with 2 subjects per group. Model will include group and time as class variables, but no interaction. So our model looks like this. And I would say in general, you know, if you're not going to include an interaction, you probably should have a good reason to not include it. But in this case, say that that's the model that we want to use. There's no interaction. We just have our alpha. This is going to relate to the group effects. This tau is going to be our time effects. And with that model, we're assuming that changes over time are going to be the same between the groups, that the patterns over time are going to be the same for the 3 groups. So that's the model we're using, but that's the assumption we're making when we do that. So we have 3 groups, H equals 1, 2, 3, 2 subjects, and 2 times. And so our beta vector looks like this. There's 6 parameters in it. And X, if we were to write that out, the first column is going to be the intercept. So what do we have there? Ben, were you going to answer? Matt, go ahead.
Just all ones.
Yeah, so the first column is 1s, and we have there's 12 of them, okay? And then we have in group, the first subject, let's say, is in group 1, so we're going to have 1, 0, 0, and then time 1. I guess I didn't need to make this so far away, because that's where we're at. So And then that same subject, we have time 2. And then we have another subject like that. Okay, so that's for group 1. And then the same thing for group 2. They're that subject's in the second group, and that's the first time. This is the second time point. A second subject in that group. And then finally, a couple subjects in the last group. Sorry, that should be 1. That's the first subject in that last group. And then second subject in that last group. Okay, so that's the X matrix. And is it full rank? No, definitely not, because we have a level for we have a column for every level, for group and for time. We didn't put any constraints in. We didn't build in a reference level or anything like that. And so if we fit our model, if we use this X, we use a less than full ranks matrix. We can use a G inverse then, but the question is what linear combination of our beta are estimable? In other words, what linear combination of those parameters are uniquely and unbiasedly estimated? So here's our question, like here's 4 different possibilities. Is the intercept itself, is it estimable? In other words, is it unique? Is the third group, is the effect for the third group, is that estimable? What about the mean plus the third group effect? And then finally, what about the mean plus the third group effect at the second time point? So these are some possible linear combinations of our parameters that we may be interested in. So
Is the intercept the mean here?
it depends. Again, we talked about that last week.
Right.
Like,
So
is it the
intercept-
overall mean? It could be, depending on, how you do things, but not necessarily.
Okay.
Could just be an intercept that's not necessarily the grand mean. So what you can do in this case, we have our X matrix, and then either in ProcIML or in R, you can compute this H matrix. So you define X, you plug that in, and you can do this very easily in either R or ProcIML and SAS. So here I've defined what H is. So it's X transpose X G inverse times X transpose X. And I've also defined these certain L vectors that we may be interested in. The first one is just relates to mu. The second one relates to alpha 3. The third one relates to mu plus alpha 3. And, so they correspond to these. So this would be for mu and so forth. And then the last one was for mu plus alpha 3 plus tau 2. So what we do is we enter those 4 possible L vectors, and then we compute L times H and see if it's equal to L. And if it is, then that's estimable, right? So
I have a quick question.
yeah,
Is it the case that, so if we look at number 3, where you're looking at mu plus alpha 3, is it the case that if you go up and look at your column vectors, and if the sum of those 2 vectors are linearly independent from the other column vectors in your matrix, then it is estimable? But if they are linearly,
I think you have to stick with this. You have to test L equals LH. I'm not sure what you had just suggested would always work. That's an interesting question that you had. But I think we have to stick with this general approach and test
Well, is
use
it,
the whole H.
how about if I say it this way? Is it the case that the summation of those two column vectors, if they are linearly dependent on a different column in the matrix, then it's not estimable?
Yeah, you know what? Let's look at that. Let's look at your question once we figure this out.
Okay.
But that's an interesting question that you have. So we'll look at that. When we compute the H matrix, and then I print out what it looks like, here's what we get for the H matrix. And then I've computed L1 times H, L2 times H, and so forth. And we get L1 times H, this is what we get here. L2 times H, L3 times H, and L4 times H. So what you do is you compare for each case, you compare LH times L with L. And so this L1 was, I'll just write over here what L was. It was 1, 0, 0, 0, 0, 0. So the question is, are those equal? Clearly not, right? So what that's telling us is that mu is not estimable. What does that mean? It means that the intercept, what you get for the intercept is not unique, and we know that. Like if you were to change the G inverse, or if you were to use a different reference level, you're going to see that the intercept changes. Okay, so it's not a surprise that the intercept is not uniquely estimable, and this is what we talked about last time, that it might be the grand mean, it might be something else. It just depends on the approach that you're taking. Okay, similarly, what about the second one was alpha 3. Can we uniquely estimate alpha 3? So the question is this equal to L times H? So the first answer here was no, the answer here is no, right? Those are not the same. So alpha 3 is not estimable. The next one, this was mu plus alpha 3. Those equal? No, clearly not. So mu plus alpha 3 is not estimable. This last one looks a little weird. It's just rounding error, really, is what's happening. You see that number is really, really small. It should be 0. So this should be 0, this should be 0, this should be 0. It's just rounding error that happened there. The question here is this equal to 1, 0, 0, 1, and then it was the second tau, right? 1, 0, 0, 1, 0, 1. Yes, those are the same. So after ignoring rounding error, so if you didn't have rounding error in there, they'd be exactly the same. So this plus alpha 3 plus tau 2 is estimable. So it's regardless of the G inverse that we use, that quantity has a unique estimator.
Hey, Matt.
Yeah.
Is that the only one that's has a unique estimator because it accounts for all possible elements in the study design. So like all of these are not uniquely estimated because they're linearly dependent, but because you have like mu, alpha 3, and tau 2, which each like cover a component of the study, is that the reason why it's estimable? Because you've like looked at enough information?
I think that's a reasonable way to think about it. Yeah, I think that's a reasonable way to think about it. And we also know that how can we express that? We know that if we compare the means model and the effects model, we know that something that looks like this, if we define a mean that involves a group and time, that's equal to mu plus alpha h plus tau j, right? So I think it's not too much of a surprise when we compare the means model to the effects model, that if we take something that involves the intercept plus a group effect plus a time effect, that we would be able to estimate that, right? And so yeah, I think Matt, what you said makes sense. I think that's a good way to put it. A lot of times when you compare two means to each other, we'll see that that's estimable. So if you compare, let's say if we compare mu h hj versus mu h prime j. So if we can estimate, so this is a mean for one group at time j, this is a mean for another group at time j. So if we can estimate those two things, we should be able to estimate the difference, right? So that's going to be, if we compare those two, the intercept will go away, right? The time will go away because that's going to be the same effect. And we end up with alpha h minus alpha, sorry. Alpha h prime. So anything that has a form like that where we're comparing two groups at the same time or comparing two times within a group, those kind of effects are usually estimable as well. So these things are estimable. So what this does is it just gives us a foundation for understanding what we can estimate. Okay, so you do have a homework question that also asks about estimability, and hopefully this exercise, like I said, I know it seems kind of weird, but it becomes natural once you practice it and you understand the point of all this stuff. So any questions? Any other questions on this?
Yeah. Can you remind me of the big picture again, why this is important when we could just do something that was linearly independent? I know you mentioned it earlier, but I just want to wrap it up again.
Yeah, that's a really good question. You know, that's, you know, I would ask the same thing. It's like, why can't we just go back to what we did? Well, how do you know what you did before is okay? How do you know you can drop the column? How do you know that that it actually had a question? Let me see if I can pull it up from a previous homework. I didn't put this on this year's homework. If I go to homework from last year, so in 6612, you may have been told that for a class variable in a general linear model or a linear mixed model, you need to pick one level as a reference, and that the estimates for the other levels become a comparison to the reference. So using concepts of estimability in a less than full rank model prove that this is true. So my question to you is, when you set one column as a reference level, how do you know how to interpret the estimate for another level that you have in the model? You actually don't. You're told that it's a comparison to the reference level, but how do you know that? We don't really know that until we show through estimability that that's true. Okay, so you're kind of in the 6612 approach. You're actually, what you're doing is intuitive. It makes sense. You have a reference level, you get estimates, and then you're told, well, what you get for another level is just a comparison to the reference. How do you know that until you walk through the bigger picture of understanding if we had a less than full rank model and then showing what we can estimate? It's then that you can show that, yeah, the estimate for another level becomes a comparison to the reference. So this really gives us the foundation to understand what we were doing before. That's one of my responses to your question. The other one is, this gives us a way to run a model, to fit a model without having to create dummy variables and without having to create a reference level. So this gives us a way to do that. It gives us a way to deal with any possible linear dependencies, sorry, that we have in our X matrix. Whether or not we understand they're there or not, it gives us a way to deal with them in a general linear model or linear mixed model. So those are my two responses to that question that you have. Any other questions on this? So yeah, it's stuff that is very foundational material, and I struggle every year. I struggle with how much to teach this, because I feel like if I say something, then I need to explain what I said in a little more detail. And I feel like the 6612 approach is fine, but it doesn't give you the big picture of what's going on with estimability. So it's a way of, for statisticians in particular, we need to understand the mechanics of the model and what's happening, and not just take things on faith in this case. So I think it might be good, we can talk more about this if there's other questions. Think about it a little bit more, do the homework exercise that's related to it, and see if you have further questions on it. So that's estimability. The other thing I wanted to talk about really quickly, because I do want to talk a little bit about degrees of freedom. I don't mind if we get through that a little more quickly. So the basic idea that I want to get through, this is another supplement, and both these supplements are, I'll have these posted, and especially after I annotate them, I'll post these on Canvas. So last time we talked about writing estimate statements when you have class variables. And it's pretty intuitive, it's pretty straightforward, because if you have a class variable, let's say with 3 levels, then you have 3 coefficients or 3 possible values that you can, enter a value for. So for example, if you want to estimate something in the first group or the first level of a group, you would put a 1 and then a 0 and a 0. So you just indicate which level that you're interested in estimating. How do you do it though if we have a continuous variable? Well, the way that you think about it is, again, like for a model, and in this case I'm talking about Boulder data. Does anybody run this race? One person? Chloe, is that it? Anybody else?
It's really fun.
Yeah, it is fun. It's like, it's a circus too. Like you'll pass, as you're running, people like will put slip and slides and stuff that you can, slide on. There's people playing music, it's really quite an experience. I've done the race a bunch of times. Actually, the first time I ran it was like in the early 1980s. So back when, I think the first year it started was like 1979, and it's grown. It's a huge race now. But what I did was I took the finishing times, and I studied like how the times changed by age. So X is age, Y is finishing time, and in this case I fit a quadratic model to the race times, and then down here you can see. So these are like the top five times by age for the men and women, and I fit a quadratic, and I allowed an interaction term so that men and women could have different fits. So they're pretty tight fits when you're looking at the top runners. And the model that we have for that I've expressed here. Okay, so here's our model. And so we have X is equal to age, Y is race time. Alpha is our gender or sex, however you want to think of it. So this is the that would just give us intercept differences between men and women. And then we have the interaction pieces here. And there's two terms because I've allowed a quadratic in the model. Okay, so you can think of, if we just had one, or if we pulled them all together, then we would just have this part, our quadratic. But because we have men and women, we're allowing different interaction. We can think of these as, the deviations that we have. And if we have a reference level, then it could be the deviation for either the men or the women, depending on who's the reference. Okay, if we take that modeling approach. So if we write the less than full rank model, if we put in a column for every level, then we have the intercept, and then we have age squared, and then we have a column for both the men and women. So this is a full rank model. I'm putting in columns full for both the men and women. Sorry, less than full rank. So it's kind of weird, that name, less than full rank, because the less than full rank X has more columns, right? So it seems kind of backwards, but a less than full rank X is actually gonna have more columns because you're putting in a column for every level of every class variable that you have. So we have the intercept, we have age squared, column for each of the men and women, and then the interaction column. So this is the basic form for X. We have our beta vector, and so you can fit the model. And then I had asked this as a previous homework question. You can take this information from your parameter estimates and actually write out what is the quadratic equation that applies for the men, what's the quadratic equation that applies for the women, and they're different because we're allowing different intercepts and we're allowing different interactions. And so essentially they have their unique quadratic functions that we can express. So I've taken the parameter estimates and I've combined the information so that we can write them out that way, and then plotted them here. The question though is, how do you, like, if there's specific estimates or contrast statements that you want to write, now that we have continuous age, how do those compare, you know, to the previous approach that we did? We actually have one class variable, so gender. A lot of people say sex should be the name for that now. So, and distinguishing that, but here I've written it this way before a lot of these ideas came up. So, so that's a class variable. So I have gender in the class statement, and that means that we're going to have a separate column for the men and women. Okay, and that's treated as a class variable. So you can think of the first level is, so I've defined it up here probably. One for male, two for female in this case. So the first column is for men, second column for women. It's you have to keep track of that though, because like if you use M and F as the letters of that variable, then the females would actually be first because that F comes before M in the alphabet. So you just have to keep track of which level is first and which is second. So if we're comparing at age 45, the men and the women, we end up with an estimate statement that looks like this. How can you figure out, you know, why does age drop out? Well, because we have age 45 for the females, age 45 for the males, it's going to be the same. So that term falls out. But we do have the other terms that don't fall out. And again, like I talked about last time, one of the easy ways to do this is to actually figure out what is the estimate for the women at age 45? What would all the coefficients be? And then do the same thing for the men. Take the difference, and then it becomes clear which ones are falling out, which ones are not falling out. But since we have a continuous variable, which is age here, when we consider L beta, in this case, we're taking a linear combination of our parameters. When you have a continuous variable, it ends up being the value of that variable. And that's why we put in 45 for X here, okay? So you're treating a continuous variable different than you do for a class variable. You put in the actual value that you're interested in using for a continuous variable. In this case, it would be 45. We want to say, you know, we're asking the question, at age 45, what is the difference between the men and the women, right? So we do have gamma 1,1 and gamma 1,2. For the men, it would be the first level, so that'd be 45 and 0, and for the women, it'd be 0 and 45. So when you take the difference, it ends up being 45 and then negative 45. Okay, and a similar thing for the gender by age squared term. Okay, so I think a good way to think about this information is to get the form of L beta for continuous variable, you plug in what the value of X, the relative value of X should be. For a class variable, you put in a 1 for the particular group that you're considering and a 0 otherwise. And then when you end up taking a difference between the two, you often have something like this, a 1 and minus 1. Okay. Any questions on that? Or is this more review? Is this pretty straightforward? I didn't see any nods this way or this way from anybody. So maybe
one quick question.
Yeah.
What's the 2025 again in the last statement?
That would be, So we have x is 45, right? And in those last terms, we have an x squared. So that's
Oh, okay.
45 squared. That's
That
where
makes sense.
2025 comes from. That's a good question. So we have in the homework, there's some questions. I can actually come up with some more practice questions for both the class and continuous if it would help you guys to practice some of these. I can prepare some practice questions. So I want you guys to be fluent. Honestly, I want you to be fluent in writing estimate statements and contrast statements, whether you have class or continuous variables. And so if it requires you practicing more, let me know on that. So I see some thumbs like, so I can do that, you know, beyond just the homework, maybe like getting 10 or 15 practice questions on this, because this is like over my career, I would say the biggest thing you can do, like as a statistician or somebody that's quantitative, is to understand how to write custom tests that you are interested in, and not just running some software code, getting the output and saying, okay, here's what I get and here's what I can interpret. A lot of times you will have research questions that are specific, more specific, that you need to write your own custom tests for. And so I think a lot of people, like in practice, maybe won't do it, and they'll just end up using whatever the computer output shows them. But we want to be able to write our own tests, specific tests that are related to our own research questions of interest. So I think it's pretty important. So the first two, yeah, somebody have a...
If you have because sometimes I've seen it like for the first estimate statement you have, I've seen like 1 0 versus 1 -1.
Yeah.
Does it change depending on whether you have write a less than full rank model versus a full rank model?
It can, yes, definitely. Okay. It can, but I think to be safe, like we could have done this if we would have known that we're using the second as a reference level, like how SAS typically does it.
Yeah.
Right? You may get the same estimate by just saying 1 0. That's a good question, but I think this is safer because this will cover all possible cases. And just in case you didn't have the same approach where the highest level was the reference. We know that's how SAS does it, so we know that would have worked out that way. But I think this will answer all possible cases, so that this is probably a better way to write it. And intuitively, it kind of makes sense that we're comparing genders, we're comparing men and women, right? So I think intuitively that looks better as a comparison between the men and the women. Okay. But that's a really good question. So the first two I wrote were specific estimate statements. So we get an estimate and we get a t-test for that. If we have a case where we have multiple rows, so if we're testing C beta equals 0 versus the alternative that they're not equal, then we're dealing with contrast, right? Because in this case, you can see we have multiple rows. There's going to be 2 rows because we have the term that we're considering, and then we have the coefficients that we need for that, and then a comma, and then here would be the second row. And so this specific test, we're comparing for this term here, that's the gender by age, and then the gender by age squared is this term here. If those are equal, so gamma 1 1 equal gamma 1 2, and these two are equal, there's no interaction at all, right? There's no linear interaction, there's no quadratic interaction. So this is an overall interaction, any type of interaction, linear, quadratic. And so the null hypothesis would be that there's no interaction. So that's saying, are the changes over ages, or the differences between ages, are they consistent between men and women or not? And so that's a test for interaction, but that doesn't consider intercept differences. If we were to also consider intercept differences, we add this term to compare gender, the main effect for gender, right? Or the, not really main effect, but it's intercept difference for gender. Main effect would really be comparing men and women at the average value over ages. Okay, that's the distinction I would make there. So yeah, go ahead.
And this might be an obvious answer that I'm just missing, but when you have custom hypotheses tests that don't equal 0 but equal something else, ultimately you need to make an equation that equals 0 to write these like estimate statements right. So do you just impact the intercept, or like how? You know what I'm saying?
Yeah, that's a good question. Like if you're testing
like a slope equals 1 or something.
Yeah.
0.
Or CB equals something other than 0. Yeah, the way this is set up is to naturally to compare to 0. So you would have to move everything over to the left side of the equation, right? So that you're writing a test in terms of comparing something to 0. I mean, that's naturally how both the estimate and contrast statements are set up. So if there's a difference and you want to do something else, you would have to work that in to this side, like you said, maybe by modifying the intercept value or something like that.
Okay.
I'll try to come up with an example. I'll put some practice questions together, and I'll think about that as you know, that question that you had, where you might be comparing not to 0 but to some non-zero value. I'll see if I can come up with an example for that.
Thanks.
Yeah. Jonathan, we jumped over. I'll come back to your question that you had earlier on the estimability, and if you can think about, you know, like the mu plus alpha 3. My brain, this is how my brain works. I sometimes I go ahead, but then it comes back to me eventually. So I'll get back to you on your question as well. Any other questions on custom tests? I think at this point, yeah, I think just, you know, you have some on your homework that you're going to do. I will give you, I'll come up with a list of 10 or 15. And what I'll do then is I'm not going to collect them, but you can practice those, especially getting ready for the first quiz. And then I'll post solutions for that. And then you can check. But I encourage you to, you know, I know how things go, right? You kind of think about it, and then I'll just look at the solutions. I would really encourage you to do these as much as you can on your own, and then go check the solutions. But at some point, maybe later this week, I'll post those.
A quick question about polynomials.
Yeah.
When would you prefer to use an orthogonal polynomial instead of just squaring the actual value?
Good question. I typically do make them orthogonal, and the way that you do that is by centering them about 0. When you center them about 0, then you're making them orthogonal, and the benefit then is that those tests are independent of each other.
Okay.
You mean centering just the squared term? Right.
So like if you have, let's say you have, if we have time 0, 1, 2, and 3, then time squared would be 0, 1, 4, and 9, right? And time cubed would be 0, 1, 8, 27. Yeah, thanks. So those would be coefficients for linear, quadratic, and cubic tests, and you could use those. But what we typically do is we end up centering this. So if we center it about 0 and then you stretch it a little bit, you can actually use -3, -1, 1, and 3 as your coefficient. So we're centering it about 0, and then you can kind of expand it out or make it small. The reason why I expanded a little bit was so that we have integers, right? And then if you do the same thing for the quadratic and the cubic, you take those and you can get coefficients, but again, if we center those about 0, then we have orthogonal polynomial contrasts, and that way being orthogonal allows them to be independent of each other. And the other benefit then is the sums of squares adds up to the total sum of squares. When you have, let's say if we had 4 times, then if you go up to cubic polynomials, we can express the total sum squares in terms of those orthogonal polynomials. So that's a benefit of doing that. All right, so I'm gonna jump to, we have 10 minutes to do our regular lecture today. This material, I'm not as concerned about spending a lot of time because I really just want you to have the main idea. And so we have a slide set, there's 21 slides here. And I just want you to get the main idea. So I'm going to walk through the first ones a little bit in more detail, but I'll have you kind of follow up and read the later slides here. So we talked about this, how if we're doing inference for fixed effects in a general linear model, what we typically do is we make an ANOVA table and we break down the total sum of squares into sources. And then we use this information along with degrees of freedom to construct T or F tests. And we can extend the GLM to longitudinal data by making adjustments to the ANOVA table and tests. And we call that repeated measures ANOVA. Okay, but when we do inference in the linear mixed model, we generally don't make an ANOVA table. There's some special cases where we can show that they're equivalent, that it's actually equivalent. We've done that before with the simple random intercept model. But what we typically do is we build test statistics that are functions of model parameters that are, and we estimate those parameters using maximum likelihood estimation or restricted maximum likelihood estimation. And these distributions are going to have approximate T or F, these test statistics will have approximate T or F distributions. And what we do is we get the correct distribution by estimating the denominator degrees of freedom. Okay, so that's the approach for inference that we take for a linear mixed model. Although in some cases it's going to be equivalent. Again, for simpler models, it'll be equivalent to the ANOVA approach. But in general, we just have a, for complex linear mixed models, it may not be like that. It may not be like making an ANOVA table. So generally, we can think of just these test statistics that we have, and then getting the correct distribution by choosing that denominator degrees of freedom. Okay, so that's the point that I made here. So we typically are going to use T and F distributions. Why do we do that rather than using standard normal and chi-square? Is because we have unknown covariance parameters that we are estimating in those test statistics. And that's going to be the case. So when would you know the actual covariance parameters in a model? Like, you know, we develop theory and we can say, well, if you know the covariance parameters, in practice, you're not going to know it. You're going to estimate those things. And so we're going to be using T tests. We're going to be using F tests. We're going to be using T distributions, even when we estimate quantities and we do a test for that quantity, or we create a confidence interval for the related parameters. That's just how it is with mixed models. The inference involves T distributions and F distributions. And so we're accounting for the fact that we're estimating the covariance parameters. Okay, so how do we estimate the degrees of freedom? There's like 6 different approaches that we can take. And one of the reasons why I want to talk about this is, like, if you use SAS, there's methods that are used to estimate degrees of freedom. If you use R, there's different methods that they typically use. And in SAS, there's default methods. Like, if you don't say anything, if you don't say which specific method you're going to use, you know, which are the these methods here: containment, between, within, residual, Satterthwaite. You guys have probably heard about the Satterthwaite approximation. You know, if you're doing a 2-sample t-test, right, and you allow different variances, then you use a Satterthwaite approximation for degrees of freedom. It's the same principle for a mixed model. We can use Satterthwaite to estimate degrees of freedom. Kenrig-Roger. So these are some of the basic methods we can use to estimate degrees of freedom. This is where I don't want to go into too much detail. I'm going to allow you guys to read these slides and get the basic idea. I think for, you know, the question always comes up, am I going to be tested over this? I'm not going to test you over specifics on this, but I just want you to understand the basic idea. And this may impact, you know, some of the choices you make in your modeling, especially for your project that you do. And we need to talk more about that soon. So the containment and the between, within methods of estimating degrees of freedom are common in SAS, but in R you don't see these. In R you see the Satterthwaite and the Kenrig-Roger methods to estimating degrees of freedom. Okay, so you guys are probably familiar with conservative versus liberal approaches in statistics, right? When you probably hear those words and you think, I'm not conservative. I'm not voting for Trump, so I don't want to use a conservative method, right? Or vice versa. It's a little bit different in statistics. A conservative. What is a conservative method in statistics? What does that mean? Or what's a liberal method?
A conservative method, you're going to be pretty cautious about claiming statistical significance.
Right.
Whereas liberal, you might make more assumptions.
Right. So for a liberal approach would say, let's go ahead and you're allowing for more positive results, essentially, right? So conservative, you're being, like you said, like Elise said, you're being more cautious in your approach. So like for when you're, let's say you're doing power calculations, a conservative approach would be, let's go with a smaller sample size, assume a smaller sample size, that we'll get a smaller sample size, which may likely not allow us to conclude that there's differences, but if we do make a conclusion that there's differences, then we're more we can be more confident that there are actually differences. Whereas the liberal approach would be doing anything that allows you to more likely find a difference, right? So in the case of estimating degrees of freedom, we're trying to find a number of degrees of freedom that will give us the correct distribution. So would a conservative method be a lower degrees of freedom number estimated or a higher number estimated?
Higher.
Somebody said higher.
Yeah.
Okay, Chloe said higher. Anybody say lower? Matt says lower. We have one person of each. So how many say, in a show of hands, how many say higher? It would be a higher number. Okay, like 3, 4 or so. How many say lower number? 3 or 4 or so. You guys are good at balancing each other out. So you think about like, what would happen? You have to kind of think about it. Which one is going to more likely lead to a significant result is the way you have to think about it. By increasing the degrees of freedom or decreasing the degrees of freedom. Yeah, Matt, go ahead.
Like from my understanding, I don't understand degrees of freedom very well, but they kind of function the same way n does. So the higher your n is, the more likely you are to find statistically significant results. And I think of degrees of freedom the same way. So if you're conservative, you're gonna assume that you have fewer degrees of freedom, which will make it harder to find statistical significance.
That's a good answer. Yeah, that's it. That's a really good answer. And I think it can be confusing, but yeah, like think of it as sample size, right? It's related to your sample size. And if we use an asymptotic method, we're assuming infinite degrees of freedom, and that would be the most liberal approach, and that would lead to a smaller p-value and give us more likely significant result. Whereas a conservative approach would be assuming that the degrees of freedom should be smaller. Okay, and so the Satterthwaite, I'm going to jump down here to show you the estimated degrees of freedom. This would be for the fitness data, which we talked about. And you can see that in a lot of cases, they're the same. But in some cases, they're different. So for group degrees of freedom, you can see that the residual method, that's the most liberal because we're estimating that should be 40 degrees of freedom used for group. Really the best answer I think would be 8 for the group comparison. And the Satterthwaite and Kenwood-Roger go down even lower than that, so they're even more conservative than like the between, within, and the containment methods. So in a nutshell, what I've talked about is there's a bunch of methods to estimate degrees of freedom. Some are more conservative, some are more liberal. And I think, like I typically do, I'm going to start the Wednesday lecture, maybe like 10 minutes of it, and maybe just walk through this example. And I will talk about, where does the 8 come from, and why does that make sense for estimating a group degrees of freedom, and so forth for time and group by time. I'll walk through an example of that. But really for you guys, I think the most important thing is to know that that we estimate the degrees of freedom in a mixed model for our t-tests and f-tests. And there's different ways to estimate it. And further, SAS and R differ in the methods that are used in estimating those degrees of freedom. Thanks for your participation, everybody. I like the interaction. I like questions and so forth. And so there's a lot of different material we talked about today, and you guys stayed really attentive and participated. So I appreciate that. What we need to do to finish up the review material, again, I'm going to go over just a little bit more of this on Wednesday, maybe 10 minutes. And then we have random effects. We'll do that review. I promise you guys I'll get some practice custom tests, because I want you guys to know how to write tests. Like, one of the 5 most important things that you can get out of this class is being really comfortable in writing custom tests. Any other quick questions or thoughts that you guys have?
I have a question. So I thought that question about degrees of freedom, I said higher. Can you like correct my train of thought of why I thought it was higher? I was thinking that the degrees of freedom like moves your critical value higher. And your critical value of your data would be the same no matter what, but then whatever degree of freedom.
By increasing your degrees of freedom, you know, if you want to think of like an F distribution, which it starts at 0 and then it goes up positive values, right? What does that distribution look like? Let's start off. We're so close to the end. Carrie, I'll start off with this, and I'll be better prepared to give an intuitive answer to your question, I think, since we're so close to the end here. That'll be that's a good question, a good place to start back on Wednesday. So, so Wednesday we got a lot. We have the lecture and then the hour after as well. So, any other questions, just feel free to email me, but I've got in my mind what I need to pick up on, addressing some of your questions that you guys asked. So thanks, and we'll talk Wednesday.